Hi, in this video, we want to take a look at classes for data analysis in R. All right, so in this video, what we're going to do, we're going to take some code from Applied Spatial Data Analysis with R, the textbook, and this is specifically chapter 2, and we're going to run through examples to illuminate and get better understanding of the different classes we have for spatial data analysis. Now, something that's very important about data science is that we need to know what we're working with, what our options are to keep things organized. I feel like this is a feature of education for statistics, data science, data analysis, data engineering that is largely passed over. But this is really a fundamental aspect of data science. It's just knowing what I have and how I can work with it to be able to get the best result possible. If I don't understand what I'm working with, I can't get the best results out of it. All right, so we are working from Applied Spatial Data Analysis with R. This is chapter 2 material, and here is the course or the textbook's website. Now, I'm taking code from the author and I'm modifying it. And specifically, I inserted keywords and I changed the names of objects so that we have like structure, then a descriptive name every single time. And I find that that's a good way to go professionally. The author goes through and lists out all the data sets needed for the examples so that, that way you know what you're going to need to be able to work through everything. That's very nice. I really appreciate that. This data set I was unable to find though, and I'm just going to comment that out and just skip over that portion. The code is included in the video, but I won't be executing it. And here is the information for the book as a citation. All right, so the first thing I do when I get started on a project, I want to make sure that I have a clear workspace, and I want to make sure that I know where I am on my computer. So here, I'm just removing any old objects in my workspace. So don't run this unless you want to lose everything that's on your workspace. Kind of a risky thing. For this project, it's appropriate. And then I always like to set my working directory to where I'm going to be working in my computer. That way I can call things faster and easier and with shorter code. Now, there's kind of a rub to that, is that when you're using R Markdown in RStudio, a recent development is that setting the working directory, you get kicked out of that working directory after you end a code chunk. And so to overcome that, I try to use this to work through, and I feel like I'm getting inconsistent results. All right, so let's go ahead and look at some fundamental operations in R. So of course, first and foremost, R can be used as just a big calculator. And so as a calculator, we can do arithmetic functions, addition, subtraction, multiplication, division. We can put numbers to a power, to an exponent, and we have pi stored to a finite number of decimal places inside R. Now, another way to execute this same thing is I could do this. So here I'm just multiplying pi by 100 to get this number. Another way is to specify in quotations the multiplication, and then what's happening is R is treating this as an operation, as a function. And so we have open parentheses, close parentheses for the multiplication function. Then inside here, I have the things that are getting multiplied together. And here, since I want the exponent evaluated first, I can do exactly the same thing. Now here, order matters in that 10 to the power of 2. Now, and we see we get the same results. And now I can also do this across vectors. I can specify 1 through 10 and then put it to the power of 2, then do my multiplication. And so 1 through 10 to the power of 2 times pi will give me all of these different numbers. So I can, if I have a whole range of values, I could do the operation very quickly. Also, if there's a number I'm going to be using over and over and over, I'm going to use this arrow notation. So it's going to be less than a minus sign equals an arrow together. Now they have to be immediately adjacent. You can't have a space in between them, and that will define it. And when I do this, I'm telling R to remember to store the outputs. And so later down the road, I can call it anytime I want. In most applications of R, if you just have an object and you just call its name in your code, what will end up happening is it will go ahead and just print that. That doesn't always work out. There's sometimes that doesn't work the way we want to, such as if I'm inside a for loop, I can explicitly print it by going print then that. If I want to control the number of digits inside a print statement, I just say digits equal that many. I think 22 is as far out as we could possibly go. Now, something that is going to be a big deal in this video are object classes. All right, so an object class is basically a stamp that tells R how things are organized inside for an object and what functions I can use on that object. So here, the class of X, which is 100 times pi, that class is numeric. The type of is double. So it's numeric data that is stored as a double. Now, I can also go to a data set. So let's take the cars data set and call its class. Well, that's just a data frame. Also, if I go type of for cars, what is going to get printed is a list. All right, so lists are really the most flexible storage format in R we could possibly get. And data frames under the hood, we don't see it directly, but under the hood, a data frame is always a list. It's a list of vectors that are put together. And so anytime I have a data frame, it's actually a list, but it's an organized list in a very particular manner. And here are the names that we have for cars. We have speed and distance. And if I call summary, we'll get the summary statistics from our data frame. All right, so when I have numeric data in my data frame, we're going to get minimum, first quartile, median, mean, third quartile, and max. So we're going to get the quartile values for the data, and we're going to get the arithmetic average also. And what this will do, this will print the summary statistics for each column. Now, if I have categorical data stored as a factor, it'll give me a table of the most frequent levels, and if it's a character, it just says character. The structure function is one of the best ways to see what is inside an object in R. So if I have an object, I don't know what it is, I'm not sure what's in there, how it's organized, the str structure function will print that for me. So we can see if I run structure on cars, it's a data frame. I see that I have 50 rows, 2 columns, and those 2 columns are speed and distance. And I can see the first few values just giving me an idea of what's going on. Oh, and also we can see that these are numeric. Now we can also have formula classes. So distance depends on speed. And if I run class on that, R will automatically figure out that it's a formula. And if I want to, I can run a linear model where the first argument is the formula, the second argument is the data, and then LM stands for linear model, and does a quick ordinary least squares model for me. Very nice. Now, the next thing that we can talk about is binning my numeric data. Or in a lot of applications, it's hard to explain continuous data to people. If you're looking at histograms, people really don't think in that manner in terms of continuous data. Like we know that there is like a gradient, there's there's kind of like a scale going from like, let's say short to tall. But when I do data analytics, people really want simpler things to interpret. They want like short, tall, short, medium, tall, maybe very short, short, tall, very tall. They want something easier to understand. They want categories. the cut function goes through and does the categories for us. So here I'm taking the data, I'm specifying the breaks. So how do I want my data organized? And then what's going to happen is that this is going to be, it's going to set up half open intervals. So remember half open from like college algebra intervals. It's going to set that up. And so when we run this, if I had this as false, I would lose my lowest value. And so I don't want to do that in most applications. So you want to put it to true. And we can see that it gets stored as a factor. Now, when you do this, anticipate that it won't be an ordered factor. It won't be ordinal. Now, another thing I can do is I can plot. So here, if I'm interested in the relationship between speed and distance, so it should be a strong relationship. I put the formula, I specify the data, and I go ahead and put a title on there. And here I get a scatter plot, and that looks like there's a linear relationship to me. We can do box plots. Remember, box plots are 5-number summaries of minimum first quartile, median third quartile, and maximum. So here I'm looking at the distance, or where I take all the distances and I group them together by that cut function that we looked at a moment ago, and we can definitely see a relationship going on. So you notice that the boxes are shifting upward as you go from left to right. And now here I can also use that categorical data as a predictor variable. And what's going to end up happening is it's going to take averages over the entire subgroup, since I only have one predictor variable. So here's my baseline, which will be, I think, the slowest speed. And to get the average across this one, the average distance across this one, I have to add these two together. And to get the average distance across this one, I have to add the intercept with this. And across this one, I have to add the intercept with this. If you put +0, you won't have to do that intercept adding business. All right, so now let's actually look at spatial objects. All right, the heavy hitter package for this video is the SP package. All right, so this is a fundamental spatial analysis package. This works well with almost every single package in R. So this is, if you're going to be doing spatial data analysis in R, you need to know this package pretty well. Well, I mean, actually, you'll get forced into knowing it, whether you like it or not. All right, so let's go ahead and look at the first two classes. First one is a spatial class. So this is an abstract class for which useful spatial classes are derived. All right, so I'm copy and pasting help documentation here. And the CRS class is the class of coordinate reference system arguments. All right, so what this will do is this will tell R how to perform the projection when I have my data. Remember that the Earth is, not flat. I'm going to represent my data on a flat surface. There's going to be a distortion. This type of class tells R how to handle things going from the round Earth to the flat map. All right, so let's go ahead and take a look at what do we have when we look at a spatial object. Well, when I look at a spatial object, we know that we are going to have a bounding box. We're going to have a projection string. The bounding box is a matrix, and the projection string is a CRS object. All right, and we know that we have subclasses. So there will be spatial points, spatial multipoints, spatial grids, spatial lines, spatial polygons, spatial points data frames, spatial pixels, spatial multipoint data frames, spatial grid data frames, spatial line data frames, spatial pixel data frames, and spatial polygons data frames. And we're going to go over the most important ones in this list. Now let's look at the CRS class. Well, we can see that there's just one slot in there. There's the projection arguments, and it is stored as a character. All right, so let's go ahead and start playing with this a little bit. So let's do a very simple example. Let's go ahead and get a bounding box, which we know is a matrix. So I'm going to go with the most simple numbers possible, 0 and 1. And I'm going to put this into a matrix, 2 rows, 2 columns. And we specify min and max. And then for my CRS object, I'm just going to put a blank in a character. So remember, the CRS is going to be stored as a character. And I'm just going to put in a missing value as my character, just as a placeholder so we can see what happens. And so here, this is my coordinate reference system of a blank item. And so here is what it's looking like. So now if I want to create a spatial object, I need to specify the bounding box, which is that matrix I just created, and I need the projection for string, the CRS projection. And so here, if I call it, I can see that it's a spatial object. It has a bounding box, as I specified, and I have a projection string. All right, so that's not very useful. That's not very interesting. So let's do it all over again, but with a more coherent example. So now I'm going to have some different values for my bounding box. All right, so now realize that the order of this is 350 is in the upper left-hand corner, 85 is in the lower left, 370 is the upper right, and 95 is lower right. It's going left to right, top to bottom. So one thing that's important is that the entries in the matrix are going like this. So this is being treated as the first column vector. This is the second column vectors. The default is by column vectors. Remember that anytime you're working in R. And that makes more sense from a linear algebra point of view, by the way. That's why we do it that way. And then let's go ahead and specify my spatial object. I specify my bounding box. I specify my projection arguments. And WGS84 is a good default projection for most projects. And so now we can see what we've got going on. We get our bounding box, and I put in my projection. But now, there's a little bit more going on. R knew to go ahead and get all the information about the datum, the ellipsoid, the axis. All these features of the projection are taken care of automatically, easy peasy lemon squeezy. All I have to do is just put in a few letters and I get exactly what I want. So remember that we model the Earth with a collection of ellipsoids that intersect with each other. All right, so now let's talk about spatial points. All right, so the spatial points class is for possibly irregularly spaced points. So this is not a grid. This is points that might be scattered all over. So let's go ahead and get an example to work with. So I'm going to take some data from the author. And it's going to be the CRAN 051001A data set. And I need to specify longitude and latitude. So longitude corresponds to east and west. Latitude tells me my position north and south. And so here I'm just specifying basically the location of everything. I'm specifying the numbers. Now, when I'm working with a spatial points object, we have several slots. We have the coordinates, we have the bounding box, and we have the projection string. The coordinates are stored in a matrix. The bounding box is also a matrix. It's a 2x2 matrix, and the projection string is CRS like we had before. And here are our subclasses: spatial points data frame, spatial pixels, and spatial pixels data frame. Okay, so now let's go ahead and let's say I want to update my projection. So what I want to do now is, all right, I have a projection. I realize it's not the best one for my project. Maybe I need to zoom out. Maybe I need to zoom in for what's going on. Maybe I just picked a bad projection, or maybe I want to just explore different ones. So what I need to do is I'm going to go through. All right, so all I do is just include that inside my projection 4 string aspect. And I just specify my coordinates, and R will take care of the rest of forming my spatial points object. So to create it, I just go to the SP package and call the spatial points function. And so now if I call summary, I'll get some output. If I call the full thing, I'm going to get blasted in the face. I don't want to print the actual object. Most of the time when you're working with spatial data analysis, you don't want to look at what's going on directly because you're going to have a lot of points, a lot of spatial points. It'll just be too much to look at. You want to look at how it's organized and what's inside each slot. And so here I get my bounding box. When I look at the summary, it's not projected, so there weren't any alterations going on. So something that would happen is I could change the projection and it will figure out the new projection for us. Here is my projection string. And it's got 54 points. If I want to, I can grab the bounding box and only the bounding box using the B box, the B box function in the SP package. And so here's the minimum, maximum, and it's just going through the minimum and maximum of the data points I put in. And now here I can grab the projection string, going projection 4 string in the SP package. And here it is. And it gives us some warnings. And this is because I was building up things manually. Everything's good. Everything's the way I want it. So I don't have to worry about this. Now, if I want to, I can change the projection by changing the projection 4 string using this arrow notation and a new projection that I'm interested in. So here what I'm doing, I'm wiping out the projection and not replacing it. But if I had a new projection string, R would automatically figure out the adjustment for us. All right, so here I can go ahead and specify the projection that I want to be WGS84, which we defined previously in another code chunk. Now, another thing that I can do is I can specify which points are in the data set that I want. So what I'm doing is I'm taking the data where I originally got latitude and longitude. I'm looking at the data. I see, hey, I'm interested in a specific subset. I'm going to look at just the ones, I want the rows of data that are only for Brazil. And I use a which function to specify which rows those are. Well, we can see rows 4, 5, 6, 7, and 8 have a location of Brazil. And so now if I call only these numbers, so here, this is a vector of the numbers 4, 5, 6, 7, 8, and I specify that, I can get the coordinates. So if for my project I was only interested in those, or maybe I want to color them differently on my map, it's easy peasy lemon squeezy. Now, once I do that subsetting, I retain all the nice features of my spatial points. This is very nice. This is one of the most powerful aspects of R, is that I subset and everything works out the way I want it to. And so now you'll notice that my bounding box, my B box, has changed. It's automatically adjusted. And it says the number of points is only 5. All right, so now let's do another one. Let's say I'm only interested in the points where it's south of the equator. Okay, well, how would I do that? Same thing. But what I'm going to do this time is I'm going to go coordinates. I'm going to say, hey, I want to treat this as coordinates. And then what I'm going to do, I'm going to specify only that second column. All right, so that's going to specify my position north-south, and I want to be in the southern hemisphere, so I'm going to go less than 0. And so the which statement gives me that. So here, this will give me all the rows that are south of the equator. I store it in a vector, and now I can subset this. So like, for example, you'll notice the author put a negative sign there. So here, this is everything that's not south of the equator. So this command figured out all the rows for south of the equator. This says get everything but that because of that little negative sign right there. And so now let's take a look at what happens. All right, and we can see that everything is set up the way we want it to be. Here's our bounding box, and we see our projection hasn't changed, and we can see that our points have reduced. Okay, and remember that the row names by default are just going to be numbers, 1 through number of rows, and this str function displays that. All right, now let's look at spatial points data frame. Now this is where things start getting more interesting. What's going to happen is I'm going to have my spatial points, but I'm also going to have a data frame. And what's going to happen is that each row in my spatial points, each row for my coordinates matches to a row in my data frame. And so what's going to happen is that under the hood, R is going to match them up by row position. And then if I want to start working things from a data science point of view, all right, this tells me the location, this tells me the informative statistics, let's match them up so that I can do my analysis. All right, so if I'm going to do this, if I want to create a spatial points data frame, I just use a spatial points data frame function from the SP package. I specify my coordinates, I specify my data, I specify my projection string, and I say match ID equals true. And so let's go ahead and look at what we get out from this. All right, well, if I call, let's say, just the 4th row, the author just picked 4, is basically just a random one to pick. What's going to happen is that all of these are coming from the data frame port. So these entries came from the data entry, and you'll notice that it includes longitude and latitude because longitude and latitude came from the data frame. But I also have coordinates, which is coming from the coordinates parameter. And if I want, I can take a look at individual aspects. So let's say I'm interested in just the location for my data. Well, if I go $loc, what it's going to do, it's going to call that column from my data frame. And then boom, I can work with it just like any other vector in a data frame. Almost all of the data frame operations we can handle directly, and R will know to work with the data the way we want to. I can also, instead of using $sign notation, I can use parentheses instead. Notice that I've got double brackets going. So things are a little bit different than in regular data frames, but things are in spirit the same. If I want, I can sample my data. So I can use the sample function to randomly select rows from my data frame. And so here, what this is doing, this is actually picking all the rows and permuting their position. So this isn't really that interesting because the data frame stays the same. I haven't subsetted my data. I haven't oversampled my data. It just switches up the location on things. But everything is going to be, it's going to be the same data, same coordinates. They're just going to be in different row positions when I do this. So what happens is this defines a permutation on the rows. This part says, hey, shuffle around the order of my data sets. Match ID, this is going off of the rows for this. The row names are being used as the IDs, and all equal, we can see that the two spatial points data frames are in fact the same. It's important that I have match ID equals true. If I didn't have that, I would have coordinates stay the same, but the data frame would be permuted, shuffled up, and things would get screwed up. And so let's take a look at this. So here we can see that row 4 is in Brazil right there. I'm not even going to try to say it. And if I went down here, row 4 is in fact the same. So things are good. Doesn't matter which version I've got. All right, now if I start playing around with the name, so in this example, what happens is that the names are changed. So you'll notice that I've got letters. So the letters vector in R is stored, automatically comes in R, and it's just the letters A through Z. If I go through and I randomly sample the letters twice and then paste them together, I just have a new character string. So what this is doing is that this is creating junk row names on my data frame. And so what happens if I if I try to match up on ID, I'm gonna have problems. There's gonna be an error. So what I've done here is that now my data has junk row names that don't match my coordinate row names. So when I go to match the ID, it's not going to work out. So I'm going to get an error, which is just a little bit off the screen. Oh, it did not print it. Oh, darn it. Oh, phooey. All right, so you'll notice that this is a try statement. And so here, basically, what's happening is that there's an error in the code because R can't match these up. Now, if match ID was equal to false, it would go by position. So first row goes with first row, second row goes to second row, third row goes to third row, and so on. Now let's look a little bit deeper at what we've got. If I use the get class command, we can see that we've got several slots. We have data, coordinates, NRS, coordinates, VBox, and projection for string. And so data is a data frame, coordinates NRS is numeric, coordinates also is matrix, bounding box is a 2x2 matrix, and then the projection for string is a CRS object. And this extends spatial points and spatial and has subclasses. So these are subclasses of spatial data frames. And this has this is a subclass of these two, and this is a subclass of spatial points data frame. And here's the names of our column. So if I call names on it, it will give me the names from the data set. You'll notice that the coordinates, the explicit coordinates parameter is not being called. And we can create model frames using these. So I can say latitude depends on longitude, and model frame is just modeling frame for linear regression, most of the time linear regression. And here we just see that it's a specified data frame. And I can use spatial points data frame and specify it in this manner also. So I need to specify my coordinates and my data. And once again, I'm going to have everything be equal as long as I'm making sure things match up correctly. And this gives me another way of building things out. I can keep on playing with this. The author is just doing a good job of making sure we can see the different ways that we can work with this and build these objects. And so if I want to look at the structure, I can see that I have a data slot, a coordinates NRS, coordinates, a B box, and projection for string. And so we can see what is inside each slot. Now notice that I have an at instead of a $sign. If I want to call this explicitly, I need an at. Sometimes these can be a little bit harder to get at to directly. We'll want to use a special function, which we'll hit in a moment. And if I want to call the names, this is going to give me the column names of my data sets. And so, so coordinates don't have to be latitude and longitude. There are other ways to specify your location. If I want, I can specify that the coordinates are recorded as longitude and latitude. So it is also possible I could have latitude and longitude switched. I'd like to know that. And so when I do that specification, that's going to get brought into here. So it'll be in this attribute down there, and I can specify my projection, which will be stored in here. All right, so let's go ahead and use SP coordinates to get a spatial data frame. All right, so here I'm just going to run through an example. I'm going to take some data of a turtle in the ocean. All right, so here's my data set. I'm going to use CMAP 105 mod, which is from the publisher's website. Here's a summary of the data. So here I've got the ID row, I have latitude, longitude, and the date. So first thing we're going to do, we're going to convert the date to a date format. And so we can see that it's stored in there as month, day, year, and then hour, minute, second. And here is our time zone. Now I'm going to build my data frame, and I'm going to specify. So I'm taking the original data I have, and I'm going to put timestamp in the data frame as the converted time that I have. Now you'll notice that I've got time in here, time and date. I have time and date here, so it's actually redundant, but it's not a big deal, not a problem. And then here, what we're doing, we're specifying latitude and longitude. So if so some of the data is on different sides of the international date line. So to deal with that, if the longitude is less than 0, we're going to add 360 to it. So that way we can see it as a continuous movement. If I didn't do that, it would look like the turtle's going, then all the way going around the planet to just the other side of the international date line, then moving along like that. And so this is just so that we can project things correctly onto the map. And just to make sure I have everything in order, I sorted the columns by the timestamp. I'm going to specify that I'm working in longitude and latitude. I am going to set up my projection to be the good default of WGS 84. And I'm going to pull in, using system file, the GSHHSC.B in there. And this is for the purpose of plotting the map, by the way. And then I use map tools. RGSHHS is going to take this and convert it to a usable format. I'm going to call it PAC for Pacific Ocean. And we're going to plot the SP slots. I'm going to keep my axes. I'm going to color everything khaki 2. And I'm going to have I as a parameter for x-axis, y-axis. Now on top of that, so this is my map. This is going to be my data points of the movement of the turtle. I'm going to convert things. I'm going to get months for what's going on, just so I know what's, so I'll have the month number, and I'm going to have a cumulative sum, and I put in -1 for baseline aspect. And then I'm going to just have my coordinates in there. And then I put on some text throughout. And let's take a look at the actual map. And so now I can see a progression of where the turtle was as time went on. So September, October, November, December, January, February, March, April, May. Between May and June was kind of like hanging out here. And then July and August. So, that's interesting. All right, so now let's look at lines or line, spatial line, line, lines, and spatial lines classes. So a line class is a class of a line object. I mean, it's not really that exciting, not shocking. Lines, plural, is for a collection of line objects. And then spatial lines are a special class of lines. Now, contour lines are not going to be covered yet. We're